Welcome back after the break. I'm Jacinta Delhayes and this is Lee Townsend. Welcome back to the mid-morning session on the final day of the SAAA 200th Anniversary Symposium. It's certainly been a very impressive virtual conference so far, hasn't it, Lee?
Yeah, it's been excellent. I've enjoyed every day so far. A great set of talks.
Yeah, very varied.
Yeah, very varied. Something for everyone on every day, which has been great to see. A reminder again, so we have 5 talks in this session. And a reminder to please put all your questions onto the Slido Q&A part of the app. We'll try and get through them all. If we can't get to your question, please repost on the discussion section of the app.
So first up today we have Kavilan Moodley talking to us about dark energy with HIRAX 21 centimetre intensity mapping. Kavi is the PI of the HIRAX project and Director of Astrophysics Research Centre at the University of KwaZulu-Natal. Welcome, Kavi.
Thanks, Jacinta.
Take it away.
Okay, thank you very much. Just getting my timer going here. So thanks very much, Jacinta, for that introduction. And thanks to the organizers for inviting me to this 200th birthday celebration of the SAAO and the symposium. So as Jacinta said, I'm at the Astrophysics Research Centre at UKZN, and today I'll be talking to you about dark energy with HIRAX using the 21 centimetre intensity mapping technique. So shown here is a graphic of this of what we hope to finally realize at the SKA South African site in the Karoo. So let's start at the beginning with the Big Bang. So we believe the universe began in a Big Bang and was followed by a period of rapid expansion. In the early universe, radiation dominated, but eventually when it faded away, matter came to dominate, and that marked the onset of galaxy formation and structure formation. And then what we see in the very late universe is that dark energy has come to dominate, and we infer the presence of dark energy from the accelerated expansion of the universe. So at these very early times, we can actually see the seeds of structure of the structure that formed in the radiation pattern. So this is called the cosmic microwave background, and we can measure the anisotropies in the cosmic microwave background. So shown here is an all-sky map from Planck, and you can see these small fluctuations. It's these small fluctuations that eventually grew, these fluctuations that were present in the matter that eventually grew to form the large-scale structures we see today. So we can actually use the cosmic microwave background data. It's extremely precise and accurate, along with other cosmological probes to constrain the fundamental parameters of the universe, including the energy content. And so shown here is a somewhat old slide now, but showing the dark matter matter density against the dark energy density. And you can see that there's this so-called cosmic concordance, where all the observations point to a universe that's made up of about 68% dark energy, 27% dark matter, and about 5% ordinary matter. So we can ask, as much as we can measure these parameters very precisely, we can ask the question, what actually is the dark energy? And progress here has been slow, at least on the theoretical front. We don't have a good model for what the dark energy is. It could be Einstein's cosmological constant, or it could be some scalar field. None of those are well motivated, but theoretically we still need to explain, the magnitude of the dark energy in relation to these theoretical models. So what observers have been doing is getting busy with trying to go out and actually measure the expansion history of the universe and learn about the dark energy. So key probes for the dark energy are Type 1a supernova, which were used to discover the original accelerated expansion. There's also cosmic lensing, galaxy clusters, and the probe I'll be talking about today is baryon acoustic oscillations. So what are these BAOs, or so-called BAOs? So let's just start this video. So here we see an overdensity in the early universe, which is an overdensity in matter and radiation. And this overdensity moves out due to the pressure of the photons. And here we see it again. So as it moves out, it carries along with it, the photons carry along with it the baryons, whereas the dark matter remains at the center. And at some point, the photons, so the matter and the light separate, and the photons basically dump the baryons at this characteristic scale here, shown by the size of the ring, and that's called the baryon acoustic oscillation scale. And it's basically set by the sound horizon when the matter separated from radiation. So we can actually go out and look for this characteristic imprint in the distribution of matter, right? And it's actually been measured. So initially by the Sloan Digital Sky Survey. So shown here is some data that confirms the presence of this baryon acoustic oscillation feature in the distribution of galaxies. So shown here on the bottom right as a peak in the correlation function on this characteristic 150 megaparsec scale. And in the power spectrum, you see it as acoustic oscillations. So this feature has been measured. And so now our hope is to improve the accuracy with which we measure this feature, and then also to track it over the expansion history of the universe from about 11 or 12 billion years ago to about 5 billion years ago, or even down to the present epoch. So HIRAX actually uses not visible galaxies as a tracer, but hydrogen in galaxies. And the hydrogen, and so shown here is a simulation of an N-body simulation with gas and hydrogen included. And what you see is that the neutral hydrogen actually traces the gas content, so where the stars form very well. And so we can actually, instead of using starlight from galaxies, we can actually use the neutral hydrogen to map out the large-scale structure of the universe. And it's shown here as in this kind of well-known cosmic web structure. So how do we measure hydrogen in galaxies? Well, we use the 21 centimeter line. So this comes from the spin flip transition of the hydrogen atom. So the electron moves from a parallel spin state to an anti-parallel spin state with respect to the proton, and in so doing gives off a 21 centimeter photon. This is a very rare transition, and so it's a very weak signal. So we need lots of collecting area to actually measure the signal. So we can go out and measure hydrogen in galaxies. And as I said, that's very expensive because the signal is very faint. So instead, what we are interested in is a much larger scale than galaxies. So shown here is the map of the large-scale structure distribution, and each dot here is a galaxy. And you can see that the BAO scale designated by this yellow ring is much larger than the scale of galaxies, so roughly 150 megaparsecs versus 1 megaparsec. So in fact, we don't need to actually resolve the galaxies because the feature we're interested in is on a much larger scale. So we can actually sacrifice resolution for sensitivity and basically have very coarse resolution that will map out the baryon acoustic oscillation feature. And that'll allow us to also get large volumes or survey large volumes over a large redshift range and over a large area of the sky so that we can beat down on cosmic variance. So this is the technique of intensity mapping. And so, smoothing the distribution, you'll still be able to pick up the baryon acoustic feature in it. And once we measure this BAO peak, we can use it as a standard ruler to track the expansion history. So that leads us to the hydrogen intensity mapping and real-time analysis experiment. So shown here is a kind of cartoon of what the final array would look like. So our plan is to build just over 1,000 6-meter dishes that operate at radio wavelengths of or frequencies of 400 to 800 megahertz. So some of the specifications of the telescope are given here in this table. And the basic plan is to build this telescope in stages. So a scalable array, starting with a prototype, which is an 8-element prototype, then moving on to 128 elements. And in each of these stages, we plan to retire key risks to the project. And finally, to moving to the 256 stage, which is fully funded. We do plan to scale up to 1024, but have to secure the funding for that. Once we build the full array, we'll observe for 4 years, covering an area of 15,000 square degrees. To make this project cheap, we use dishes that are stationary, but they can tilt to build up more sky area. And the fabrication of these dishes is happening in South Africa. On the back end side, there's a strong overlap with Chime. So we're using the same FPGA boards to process the signal, and then we correlate with GPU, a large GPU correlator. In terms of the details of the project, so here's a graphic of the various partners. So there's a lot of international and local partners, roughly 25 in total. In terms of the funding, I've indicated that we fully funded through to 256 dishes, and we've got South African funding, both from UKZN and the National Research Foundation, and also Swiss and Canadian McGill funding. So the project is in good shape to build up to 256 dishes. Location is very important, and so we benefit from all the infrastructure investments that have been made in astronomy in South Africa. So in particular, at the South African Karoo site, we have an agreement in place with the South African Radio Astronomy Observatory, and shown here is the location for of HIRAX, and in relation to the SKA and where Meerkat is and where the SKA will be. Yeah, location, I was talking about location. So at the existing site, we have infrastructure in terms of roads, power, and data. And what's amazing is the RFI levels are extremely low. So this is shown as in our band is the RFI kind of contaminant or emission, and we see that is actually very low. And we also have the advantage of having access to southern skies as well. So we can do cross correlations with cosmological surveys from the Large Synoptic Survey Telescope and the Simons Observatory. So other HIRAXs include the Rock HIRAX. So this is the project is named after the Dassie, and we slightly misspelled the name. So when we named the project, we didn't realize there was a trash metal band also having the same name. So just quickly moving on to what cosmology we expect to do with HIRAX. So these are forecasts for the HIRAX distance scale. So as I mentioned, we'll track the expansion history of the universe. In particular, we'll measure the distance scale, which is sensitive to the evolution of dark energy. And so we aim to measure the distance scale at the percent level over a redshift range from 0.8 to roughly about 2.5. And shown here are current measurements from the EBOS. So this data came out earlier, a few months ago. And so this is the state-of-the-art measurements where you're basically using galaxies as traces. And then you can turn that distance measure into constraints on cosmological parameters. In particular, shown here are the dark energy parameters, the equation of state, and the evolution in the equation of state. And we'll actually be able to improve significantly on current constraints from other cosmological probes. And the kind of money figure is the so-called figure of merit. So the HIRAX 1024 figure of merit is roughly 300. And this is approaching the Dark Energy Task Force figure of merit stage 4 surveys, galaxy surveys, which is around 400. So even though the project is relatively inexpensive, it can have a high impact. And shown here are the contours in the W0 WA plane and what is the current state of the art from EBOS. So that's the cosmological constraints. In terms of design plan, this is how the array will be rolled out. So there'll be 1024 dishes with an active dual polarization feed an optical fiber that takes the signal back to the digital back end. So converted in with the analog to digital converters, then channelized, and a corner turn is basically done to shuffle the frequencies from different telescopes into the frequencies, all frequencies from the same telescope into so basically to channelize the data. And then the correlation is done on the GPUs. So we've been busy at Hartebeesthoek Radio Observatory building a prototype, so the Hartrau 8-element prototype, using cheap off-the-shelf dishes to test our RF signal chain and our instrumentation. We've also used the site to develop with local companies metal and fiberglass dishes with a preferable f.25 focal ratio. And so those are being tested, and we're basically doing various field tests. And we also have prototyping efforts in Green Bank and DRAO with our American and Canadian partners. So this is my final slide, just a quick upcoming schedule. And basically, I'm not going to go through all the details here, but we're still continuing with the HIRAX program this year and next year, and then we'll move to develop the site in the Karoo next year, and then build in about a year from now a 2-element qualification array. So we're putting out a tender for the dishes that will be awarded to a South African company, and then they will build dishes in stages in the Karoo site. So that's the upcoming plan, and we hope to have the 128 element at the end of 2022 operational, and 256 probably 6 months later. So that's it from me, and I apologize for the disruptions with the keynote presentation.
Thanks very much for that, Kavi. I have a question. How is HIRAX different to the Meerkat and SKA? You mentioned that they are both in the Karoo site. So what is it that makes HIRAX suitable for your science aims to measure the BAO and to study dark energy?
Okay, so it's actually in this picture here, which I hope you can see. So it's the HIRAX telescope is actually going to be a very compact array. So if we push all telescopes like Meerkat have their baselines, so the separation between dishes much larger and in a random pattern, and that allows better imaging and high resolution imaging. With HIRAX, as I mentioned, we're sacrificing resolution, and we're more interested in surface brightness sensitivity. So if you push all the dishes closer together, you get very good surface brightness sensitivity, and we're mainly interested in large scale features on the sky, so degree scale as opposed to arc-second scale. So that gives us very different science goals from Meerkat and the SKA.
Right, so a much more compact core then. Lee, did you have a question?
I do. Hi, Kavi.
Hi,
sounds
Lee.
like a really great project. Could you tell
Thanks
us a little
very much.
bit more about what happens, what effects this will have on your science goals if you don't get the full funding for the 1028 array?
Oh, so I should preface my response by saying, this is a very new area and quite competitive area. So we're still in the very early days. Maybe like the cosmic microwave background studies were 30 years ago. So these are the first stages of these 21 centimeter intensity mapping experiments, and there's a lot of lessons to be learned. CHIME has already built the cylinders, and I have been observing. But there's a lot of systematic hurdles to be overcome. And so I think with the 256, we'll learn a lot about that. We still have enough sensitivity with the 256 to deliver competitive constraints. But of course, the science would be much more amazing with the 1024.
Great, thank you very much, Kavi. That's all we have time for, but thanks for joining us.